This is section 4.6, page 3, some more related rates. Today we start doing the application of the related rates. You should have the mechanics down from the first 2 pages of this section. I'm not going to read these steps to you, but ultimately these steps are incredibly important in solving these related rates problems. Let's just move on right down to example 5. A tumor in a person's body is spherical in shape. When the radius of the tumor is half a centimeter, the radius is increasing at a rate of 0.001 centimeters per day. What's the rate of increase of the volume of the tumor at that time? So looking back to the steps up above, read the problem several times, and then the next thing is we'll have to draw a well-labeled diagram. So we need to draw this tumor, which is spherical in shape. So let me get this sphere up here. The only dimension that we have in this sphere is the radius. And while it says right here the radius of the tumor is half a centimeter, the radius is not always half a centimeter because the tumor is growing. So we don't want to label that radius with half a centimeter. The next thing that we need to do is to identify the information that we know, and we know that the radius is increasing at a rate of 0.001 centimeters per day. So dr dt is 0.001 centimeters per day. Also, we need to list what it is that we hope to find, and we want to find the rate of increase of volume. So that's dV dt, and at that time that they're talking about here is this part. When the radius of the tumor is 0.5 centimeters. Very often in related rates, the time is not, that we want to evaluate something, is not necessarily expressed as a unit of time. But for this one, we want to know dV dt when the radius is 0.5 centimeters. Next step here is to write an equation to relate the variables. Our variables are volume and radius. So the equation for volume of a sphere is 4/3 pi r cubed. And now differentiate implicitly with respect to time. So dV dt is, here's this constant multiple coming down, 4/3 pi. The derivative of r cubed then, 3r squared, times dr dt, since we're differentiating with respect to time. Cleaning this up, even though this step is not listed, we always simplify along as we go. This gives us 4 pi r squared dr dt. Now substitute in any rates and only sub in the rate that you know. dV dt is 4 pi r squared. dr dt, that rate we knew, and simplifying, dV dt is 0.004 pi r squared. Solve for the desired rate, and I'm going through the bullet list at the top. We have that already because we're wanting to find dV dt. Sometimes they'll give you this rate over, they'll give you this rate over here and ask you to solve for this one. But in this case, we're already solved for that rate. So the last part then, or nearly the last part, is to evaluate, and we want dV dt when r is 0.5 centimeters, and when we plug that in, we have 0.004 pi times 0.5 squared, which is 0.004 pi times 0.25 or 0.001 pi. Alright, not done. That's the numerical answer, but the last bit here is to write your answer in a sentence, and this is the rate of change of volume. So we will say that the volume of the tumor is increasing at a rate of 0.001 pi. Units here, these are centimeters cubed per day, when the tumor has a radius of 0.5 centimeters. And when we write our answer, it's very important that you identify the units of the rate, and you also give the when that particular rate was calculated. Please tune in for page 4.